3, 2, 1, and action.
Solutions and mixtures. What do you need to know? First, we're going to relate this back to the fundamental part of chemistry that we've been learning this unit, delta G. Delta G is equal to delta H, which stands for enthalpy, minus temperature multiplied by delta S, which is entropy or disorder. And what you need to know is that the substrate for the solutions for delta G is going to be solution. So what does that mean in the context of the signs? So what happens if delta G of solution is positive? That means it's non-spontaneous, which means that the mixture won't dissolve. Does not dissolve, right? And what happens if it's negative? If delta G is negative, that means that it is spontaneous and it does dissolve. So it's important to constantly bring it back here so you know whether something dissolves or whether it doesn't, because that's what we're trying to find here. So let's look at specific examples. Let's start with miscibility. Miscibility is when you mix two liquids together, right? And there's two different scenarios right here. The fundamental thing you need to know for miscibility is that like dissolves like. That essentially means, and this is what you've been learning from elementary school, but at a higher level of chemistry, that means that whatever IMF, if it has the same IMF, then it does dissolve. So for example, H2O, water, this has hydrogen bonds. Ammonia, NH4, also hydrogen bonds. These two will dissolve. That means these are miscible, right? Whereas H2O and oil, they won't dissolve because oil has primarily covalent dispersion forces, right? So since the IMF, the primary IMF is different, they won't dissolve. So it's important to look at the intermolecular forces, and if they have the same intermolecular forces, then they will dissolve, and if they don't, they will not dissolve, which is important. And an application of this is when you look at soap. So soaps have two layers. They have a hydrophobic layer and a hydrophilic layer. The hydrophilic layer essentially attracts molecules that are polar, so like water, for example, whereas the hydrophobic layer will attract molecules like oils or fats, which have primarily dispersion forces, which is why soaps need both of these, because you might get both polar and non-polar substances on your hands that you need to get rid of, right? So it's important to look at this primary thing, like dissolves like, in the context of intermolecular forces. So that's how liquids mix with liquids and to form solutions and mixtures. So what about salts? What about solids? So salt dissociation is a little bit different, but what you need to know is you always bring it back to that delta G equation. Does it dissolve or does it not? So delta G of solution is equal to delta H of the solution minus temperature multiplied by delta S or entropy. So let's start defining some of these variables here. What is delta S? Delta S is entropy. So when you mix a salt or any substance into a liquid, what happens to the entropy overall? It increases because there's more molecules, there's different types of microstates that are possible. So delta S will increase. That means delta S is positive. So knowing that we have this delta S is positive in every single reaction where a solid or a salt is added to a liquid, now the main thing that determines what G is delta H. Is delta H positive or negative? So how do we figure that out? In the case for salt dissociations, we can further split delta H into delta H is equal to the delta H of the lattice energy minus delta H of the hydration energy. So what are both of these concepts? They're pretty easy to summarize. So delta H of the lattice energy is the energy required to break the lattice energy bonds between two different ions, whereas the delta H of hydration is the energy required to create intermolecular forces between the ions and the surrounding liquid. Primarily, it's going to be water, right? So let's do an example just to make this a little bit easier. So you have NaCl. This is an ion. You put this plus H2O, right? And what happens is NaCl is these lattice energies start breaking because of the mixture, and it will be Na plus and Cl minus, right? This breaking point, this is an endothermic process because breaking bonds is endothermic, and this ionic bond is being broken, and the energy required to do this is delta H of Cl, the delta H required to break the lattice energy. And eventually what happens is these water molecules start surrounding these two compounds and they start hydrating them, right? So you have water molecules here and they form ion dipole constants or energy intermolecular forces between these. And these ion dipoles, they're new intermolecular forces that are being created. So what happens when you create a new intermolecular force or a new intermolecular bond? You have an exothermic reaction. It requires energy to create it. So, or it dispels energy to create, which is why the delta H of hydration is an exothermic process, so it's negative. So now we know what both of these concepts are in terms of salt dissociation. How do we figure out what the overall delta H is? We simply just need to figure out whether this is positive or negative, right? So, or which one has a greater magnitude? Is it the delta H of lattice or the delta H of hydration that is bigger? Because that will result in our total delta H value, right? So let's say that overall the lattice energy is bigger. So the energy required to split these is bigger. What happens in that case? That means delta H is going to be positive, right? So if you have a positive delta H minus temperature multiplied a positive delta S, so this is going to be a positive number subtracted by temperature multiplied by another positive number, so just subtracted by the temperature essentially, multiplied by a certain number, right? Another number. So what you need to figure out is that in order for delta G to be negative, in order for this reaction to be dissolving, you need the temperature to be high. So if delta H is positive, so if it's an if this has a higher magnitude and delta H overall is positive, then you will have a higher temperature for dissolution. Higher temperature dissolves. Now let's talk about the opposite scenario. What if the delta H of hydration is high? And this is low. That means this is negative. So then you would have your overall delta H value would be negative. So it's a negative number minus another negative number, which means that at any temperature, it dissolves. So that's important to know. So if the hydration energy is higher, then at any temperature, the salt dissociation can occur. But if the lattice energy, or the delta H of lattice is higher, then at a higher temperature, the dissolving will happen. So that's salt dissociation. Now let's go into gas dissolution. So gas solution, we can relate that back to the delta G equation, but the primary thing you need to note here is that delta S is going to be different. In both mixing liquids together and mixing salts, there's more microstates because it's different molecules that are mixing together. So delta S is positive for both liquids and solids and liquids. But for gas and liquids, you have a delta S that is negative. Why do we have that? We have a delta S that is negative because when you have a gas that has so many different microstates and you force it to go down in a liquid, the liquid will constrain the microstates that the gas has, essentially overall decreasing the number of disorder and decreasing the entropy, right? So we know that delta S is going to be negative within the large scheme of things, right? So what are the different situations that can happen when you have a gas dissolution? So the first one is going to be a like dissolves like type situation. So you have a gas that is polar or it has hydrogen bonds and it mixes with water, it will dissolve into the water, right? So that's pretty similar to the miscibility, and it will dissolve into the water, but you need to know that even if it dissolves, the delta S is still going to be negative. So make sure you keep track of that. And then another thing you can happen is a reaction. So the gas that is mixed with water or any other liquid for that matter reacts. So a common example that is used is the creation of bicarbonate. So when CO2 is mixed with H2O with water, you get a product bicarbonate. And this actually happens in our oceans, this happens in our bloodstream as well. So this product this is an example of a reaction. So this is still means that there's some kind of reaction. The CO2 does end up dissolving the water, but it ends up becoming a different product. It doesn't become like an aqueous ion, for example, right? And then if you have an inert nonpolar gas, that first fact still remains consistent. Delta S is negative, but what's important to know is that inert nonpolar gases will only dissolve slightly. And the reason they dissolve slightly is because delta H is negative. right? Delta H is negative because if inert nonpolar gases will have some sort of dispersion force, right? So dispersion IMS will be created between the liquid and the gas, means, and since new bonds are being created, delta H is going to be negative, right? So because delta H is negative in the grand scheme of the delta G equation, we know that delta H is going to be negative, and we know that we know that delta is also going to be negative, so negative times a negative is a positive, so plus T. So at lower temperatures, when the temperature is low, then you have a dissolution that occurs. And that's all you need to know about solutions or mixtures.